Hello there. Today we are going to be continuing to look at free we are going to be looking at free vibration response of continuous systems. Just to refresh our memories on what we had done, we had seen that if you look at the response, the equation of motion for a simple beam, axial deformations. So, axial deformations the equation becomes this way: m bar x del squared u by del t squared minus del upon del x Ea del u by del x equal to P. And for flexural deformations, this is for axial deformations. For flexural deformations, these were the equations of motion. This is for the flexural deformations of a simple beam. The reason why I am calling a simple beam is that only flexural deformations are considered and only linear inertia is concerned. Later on in this course, towards the end of this course, I am going to be talking about what we call as a Timoshenko beam. A Timoshenko beam, not only do you consider flexural deformations, you also consider shear deformations, and in addition to the linear inertia, you also take rotatory inertia of a beam. That's known as the Timoshenko beam. So, we will look at the dynamics of a Timoshenko beam later on, but right now dynamics of the simple beam in axial deformation gives this equation, and in flexural deformation gives this equation. Of course, axial deformations you only have the simple beam. You do not have, because you only have one directional motion, and that is axial and linear. So, because there is no other motion. In flexural deformations, what happens is, in addition to flexural deformations, you have shear deformations, and plus, because it is moving like this, in addition to the linear mass, you may have rotatory mass. So, simple beam only considers linear mass, does not consider the rotational inertia of a cross section, and it neglects shear deformation. So, if you neglect shear deformation, this is what you get. And last time we also looked at the free vibration response. We fundamentally looked at the free vibration response for axial deformations, which was so this is axial free vibration, okay, and assuming that u of x t is of the form phi x sin omega t, right. I am just reviewing this. We have already done this, but I am just reviewing this because I want to move on to the next step. It is, and then once you substitute that, what you get? You get this equal to m bar x into omega squared phi x sine omega t, that is this one, and this one, if you look at it, it becomes equal to phi double prime. Note that phi double prime of x essentially is the second derivative of phi x, and now if we divide throughout by phi x and sine omega t, okay, so I am going to divide throughout by phi x sine omega t. What you get is the following. You get it equal to minus, I am going to actually divide throughout by m bar Ea. So, you get m bar x omega squared minus E. Well, let me just put it this way. Let me put this phi x sine omega t is equal to Ea phi prime x sine omega t. Okay. I am going to just put these two together, and then what we get is the following, that minus m bar x is equal to the following, right. I am going to say that this is, I am going to divide throughout. Oh, sorry, I made a mistake here. This is not sine omega t, this is y of t, right. So, if you look at this, this one is y double dot of t, and this one is y of t, and so, sorry here, what we get is minus 30 plus mx phi x y double dot of t is equal to Ea phi double prime x y of t. So, if we divide throughout by phi x y of t, then we get the following. We get m bar x y double dot of t upon y of t is equal to Ea phi double prime x upon phi x. And note that if this is equal to this, which is function only of x and this is only a function of t, this is c, right. So, once we have that kind, I will call that as minus c for obvious reasons, and then what we get is we get the following equation, m bar x y double dot of t plus c y of t is equal to 0, and the other equation becomes Ea phi double prime plus c phi of x equal to 0. These are, this is what we get. Okay. Now, note that if you look at this, c upon m bar is obviously equal to omega squared, because that is what you get from this equation. Okay. So, therefore, this one then becomes equal to Ea phi I prime, okay, plus, now since this is omega, c is equal to m omega bar squared, this becomes m omega bar squared phi x equal to 0. Okay. In other words, I can rewrite this as phi prime plus, and I will call this b squared phi x equal to 0, where b squared is equal to m bar omega squared upon Ea. Okay. And having done this, then your phi of x becomes equal to b sine, a1 sine b of t plus a2 cosine b of t, and note that this is going to be subjected to boundary conditions. So, if I have this situation where it is not allowed to move and it is a thing. So, then this becomes phi at 0 equal to 0, and over here since your it's basically actually equal to P is equal to 0 and P is equal to EA del u by del x equal to 0, and so basically del u by del x. So, that means in this particular case phi prime x equal to 0. If we plug these into this, what do we get? The first one, phi 0 is equal to 0 implies that A2 is equal to 0. So, that means phi 1 x is equal to A1 sin B x, sorry, this is all x, Bx. Okay. Now, if you put phi prime, so this basically becomes what? Phi prime is equal to B A1 cosine Bx. So, that means B A1 into cosine BL is equal to 0. Now, note B is not 0, A1 cannot be 0. This implies that cos BL is equal to 0, and therefore, you get the situation that BL is equal to 2n minus 1 pi by 2. Okay. That is for this particular situation, and in this particular situation you get the situation that this BL is equal to, and once you get this becomes what? If you look at that means B is equal to 2n minus 1 upon 2 pi by L, and once we substitute the fact that B squared is equal to m bar omega squared. So, therefore, we have the situation that omega is equal to EA upon m bar square root into B, and so therefore, your omega in this particular case becomes equal to the following. Omega is equal to 2 pi n upon 2 pi over L into square root of EA by m bar. So, that is for axial, that becomes the omega, and for each omega. So, therefore, if you put n equal to, this is n equal to 1 to infinity, okay, and therefore, omega 1 is equal to pi by 2L root A by m, and therefore, if you look at the corresponding phi x, it is equal to sine pi x by 2L, that is phi 1 of x, and same way we have already looked at that. So, basically phi 1 is this way, where all the displacements are in this direction. I am actually plotting u with x, that is all I am plotting. Actually, they are in this direction. Okay. So, this is the first mode. The second mode, where omega 2 is equal to 3 pi upon 2L EA by m bar, and phi 2 x is equal to sine of 3 pi x upon 2L. This thing becomes, where this is 1 and this is u. Okay. The u is in this direction actually. So, similar way you can find this out. Now, one important point. So, this is the omega and phi, and note that this is almost identical to what we have generated even for multi-storied structures. One important point to note is that I'll only show the mass orthogonality, because in this particular case the stiffness orthogonality becomes a little bit tricky, and I don't want to go into that. It's actually fairly easy to do it, but I don't want to go into it. It's easy to look at a kind of a situation. So let's have a situation. Let's say that, well, let's take this. So I'll call this Vm. Vm, if you look at it, is equal to phi m into sine B1x, and similarly if I call this Vn, it's equal to phi m, and there's going to be a y sine omega 1 t phi mx, and this is going to be phi nx yn, this is ym, phi nx yn of t sine omega n of t. This ultimately is my displacement in the nth mode, and this is the nth mode. So if we look at this, if we get an inertial force due to this load, okay, and call it what? We'll call it Fin, an inertial force due to this load, this displacement, I'll call it as phi im. What would phi im be equal to? If you look at it, it would be equal to, this is Vn x of t, this is Vm x of t, this is also phi in x of t, this is at a particular point, this is going to be equal to m bar dx, that's the mass, into Vn x of t double dot, and similarly this would be equal to m bar x dx into Vm x of t, because this is the acceleration. Okay. So if I look at the acceleration, this is going to be equal to what? It's going to be equal to Vn is actually, if you look at Vn is given in this form. So if you look at double differential, it will become minus omega n squared m bar x dx yn phi n x sine omega n t, and similarly this one would be equal to minus omega m squared m bar x dx y m phi m sine omega m t. Okay. So these are the now what does Betty's law say? Betty's law says that if you have Fin undergo Vm over the whole length, okay, this is equal to, over the whole length, phi I m is equal to Vn. In fact, Betty's law says the work done by the inertial forces given by this undergoing these displacements is equal to the work done by these forces undergoing these displacements. That's what Betty's law says, and so that's what we've done. So if you look at this, if I plug it in, what do I get? I get Fin, I'm going to substitute, and Vm I'm going to substitute. So I'm going to get equal to minus omega n squared ym yn, because both of them, ym comes from this, yn comes from this, omega n squared comes from this. This is going to be equal to m bar x phi n x, okay, into, of course, in this particular case you have sine omega mt and sine omega nt. So, here sine omega nt and sine omega mt, that will come outside. It's going to be equal to phi nx phi mx dx, right? And then the other one is equal to minus, and here we get omega m squared, because this is the inertia, omega m squared, and we get ym yn, m coming from here, n coming from here, sine omega mt sine omega nt, integral from 0 to L m bar x phi nx phi mx dx. Okay. So, if I put these two, all these terms are the same. So, if I put it in, I get the following. I get omega m squared minus omega n squared into all of this ym yn sine omega mt sine omega nt 0 to L m bar x phi nx phi mx dx equal to 0. These cannot be 0. Automatically this implies that 0 to L mx phi nx phi mx dx equal to 0. This is the Mars orthogonality condition that we have for this thing. Okay. So, this is what you have, that you have this particular thing. Okay. So, this in essence is orthogonality condition. This is a Mars orthogonality condition that I have derived. In same way we can derive, but it just gets a little bit more complex, and there is no need to, all I say is that we know that the orthogonal, the mode shapes are orthogonal in this particular case. Okay. So much for the your what you may call it, your axial deformations. We have derived this. Last time we had looked at all of this. The only thing that we had not looked at was the orthogonality condition. Last time I stopped by looking at the equation that you are going to get if you have flexural vibrations. So, now I am going to start looking at flexural vibrations, free vibrations, flexural free vibrations. We are going to look at free vibrations, and in this particular case what we will do is we are going to be looking at specifically how to derive it. We will derive it from first principles, and then we will start seeing that different boundary conditions, how they become differently. Okay. So, let us look at it. What does the equation look like? It looks like, and I am going to take it for uniform case. So, uniform case, you have this plus m del squared v by d. In actually it is d squared, but since ei is a constant, so we can take its inside. Okay. So, this is the equation, and v of x, which is a lateral displacement, we take it equal to phi of x and y of t. So, if you look at it, the fourth order derivative here would be equal to the fourth differentiation of this into y of t, and del squared v by del t squared is equal to phi x into y double dot of t. So, putting these in here, what do I get? I get it equal to the following, and this becomes ei phi fourth x y of t plus m bar. Now, this one I am not going to put it as x, I am going to leave it as m bar, it is uniform beam. So, it is m bar into phi x into y double dot t is equal to 0. So, I can put it this as the following. I can say that look, it is phi fourth x y of t plus m bar upon E I phi x y double dot of t is equal to 0, and then if you plug this in, what do we get? We get it equal to the following. I am going to divide throughout by phi x y. So, this becomes the following: phi fourth x upon phi x plus m bar upon E I y double dot is equal to y of t is equal to is equal to 0. So, then if you look at this, this upon this is equal to minus of m bar upon E I, and obviously we say that this is equal to a term which I am going to say is equal to a to the power of 4. I am going to put it in this fashion. Okay. So, if I put it in this fashion, let us see what happens. Okay. What I get is the following, that one equation makes it the following, that is that y double dot plus E I upon m bar a fourth, right. If you look at this, this is equal to, I will take E I, over here. So, it becomes E I m fourth into y dot of t. Okay. So, omega squared is this. So, if you look at is equal to 0, and so obviously you have a situation where omega squared is equal to E I upon m bar a fourth, or we can say that a fourth is equal to, I mean either way, I mean let's not go, let's just go with this. Okay. Or we can say the other way. Okay. So, if we do it this way, obviously y of t becomes equal to a1 sine omega bar t plus a2 cosine omega bar t, and this a1 and a2 can be found out from the initial conditions, blah blah blah. Let us look at the other one. The other one says what? It is equal to phi fourth minus a fourth phi is equal to 0. Now, let us substitute a situation where phi of x is equal to c to the power of e s x. If I substitute this into this equation, note that phi fourth becomes just s fourth. So, this basically becomes the following. It becomes c into s fourth e to the power of s x minus c a fourth e to the power of s x is equal to 0. So, what we have is, we have the situation, since c to the power of x, which is in both cases, cannot be equal to 0, it implies that s fourth minus a fourth is equal to 0. This implies s squared plus a squared into s squared minus a squared is equal to 0. So, s is equal to plus minus a and plus minus I of a. These are the 4 roots that you have. So, essentially phi of x becomes equal to c1 e to the power of ax plus c2 e to the power of minus x plus C3 e to the power of I a x plus C4 e to the power of I a x. Note that minus I x. Note that we have already seen that this can be, since this is a real quantity, this has to be a combination of sine and cosine. Similarly, this one we can write it in terms of sine hyperbolic and cosine hyperbolic, where cosine hyperbolic is e to the power of x plus e to the power of minus a x by 2, and sine hyperbolic is equal to e to the power of a x minus e to the power of minus a x by 2. So, those are the sine hyperbolic functions and cosine hyperbolic functions, and if we write it this way, this becomes the following: B1 Ax, sorry, these are all Ax. Okay. So, essentially that implies that for the flexural vibrations, the phi of x is of the form, let me write it down properly again, it is equal to B1 sine A x plus B2 cosine A x plus B3 sine hyperbolic A x B4 cosine hyperbolic A x. Okay. So, now if you look at this, this becomes the following, that so that means how do I get B1, B2, B3, B4 and A? Well, what happens is you have 4 boundary conditions, and so for the 4 boundary conditions you can find out 3 of these in terms of 1, and you can find out the frequency equation, which is the A, you will get A. Now, let me take, so this boundary condition depends on what kind of a system. Let us take a basic simply supported beam. What are the boundary conditions? Well, I know that phi at 0 is equal to 0, phi at L equal to 0. I also know that since moment is equal to 0, that curvature here is 0, and I also know that curvature here is equal to 0. These are my boundary conditions that I have. So, I am going to substitute these boundary conditions into this equation. So, let us see what happens. Well, let us see the first one. The first one becomes the following. We get a situation where, since this is moment, it's actually EI phi prime, but does not matter, it's phi prime. Okay. And ultimately, let me just put this next page on here. I am sorry, I already have a page. Having put a page, so what do we get? Having put phi equal to 0, this implies that B1 sine A0 plus B2 cosine A0 plus B3 sine hyperbolic A into 0 plus B4 cosine hyperbolic A0 is equal to 0. This we know from the first boundary condition, which is phi 0 equal to 0. Now, note that this is equal to 0, this is equal to 1, this is equal to 0, and this is equal to 1. So, basically what we get from this is that B2 plus B4 is equal to 0, and this implies that B4 is equal to minus B2. Okay. Now, let us put the following. Let us put now differentiate this. If we differentiate this, phi prime of x is equal to b1 into a into sine ax minus b2 a into, sorry, this is cosine ax and this is into sine ax. The other one b3 a cosine hyperbolic ax plus, sorry, this is going to be equal to plus b4 a into sine hyperbolic ax. Okay, that's plus, huh? This is not minus. And then phi double prime x is equal to minus b1 into a squared sine ax, okay, and minus b2 a squared cosine ax, and this one becomes b3 a squared sine hyperbolic ax plus b4 a squared cosine hyperbolic ax. Again, phi double prime is equal to 0. So, this implies the following, that phi double prime 0 means minus this b1 disappears. So, it is going to be minus b2 a squared, then this sine hyperbolic disappears. So, you have b4 a squared is equal to 0. This implies that b2 is equal to b4. Now, the only way that both b2 is equal to minus b4 and b2 is equal to b4 is if they are equal to 0. This implies that these two boundary conditions imply that both b2 and b4 are 0. Okay? That is what this implies. Okay? So, now let us plug in. So, we have got this. So, essentially both b2 and b4 are not there, and so phi x is of the form b1 sine ax plus b3 sine hyperbolic ax. This is what it becomes. And now let us substitute the two, which is what? Phi of L equal to 0 and phi of double prime L is equal to 0. So, if I put this in, phi of L, all it says is that if we look at it, it becomes equal to phi 1 L becomes b1 sine AL plus b3 sine hyperbolic AL is equal to 0. Now, the phi double prime, note that when I double division this becomes minus a squared b1 sine AL and then plus a squared b3 sine hyperbolic AL is equal to 0. Okay? So, this is what we get. So, if I now put a squared and a squared here, all we get is if we add this disappears, and what I get is that b3 sine hyperbolic AL is equal to 0. Now, note that sine hyperbolic AL is not equal to 0. Okay, by definition, okay, e to the power of AL minus e to the power of minus AL upon 2 cannot be equal to 0. Okay, so therefore, this implies that B3 is equal to 0. So, from the third set of boundary conditions, what I get is that, look, the only form of phi x is equal to B1 sine AX, and then obviously that phi L tells us that, look, it implies that B1 into sine AL is equal to 0. Now, since B1 cannot be equal to 0, because if B1 is 0, then this becomes a trivial solution. Okay. So, therefore, it has to satisfy that sine AL is equal to 0, and the way sine AL is equal to 0 is if it is equal to n pi. Okay. So, if it is n pi, then you have the situation that where n is equal to 0, 1, 2, blah blah blah, n. Okay. Of course, the 0th term does not exist. So, we always start from 1. Okay. N has to be 1. Okay. And so, therefore, you have a situation where A1 is equal to n pi by L, and note that we had written earlier, going back to where we had defined this. If you look back, we had written that A fourth is equal to omega squared is equal to E I upon m fourth. So, if I write that down, then it becomes omega 1 squared is equal to E I upon m L4, and what we get over here is n is already done, pi fourth. Okay. So, what we get is that omega n is equal to square root E I upon m bar L fourth, and we have n pi squared. Okay. So, that is n pi the whole squared. Okay. That becomes omega n, and the corresponding phi n of x is equal to sine n pi L x. That is the corresponding one. Okay. So, this is for a simply supported beam, and if we put that equal, then what we get, if we were to put the first one is equal to omega 1 is equal to pi squared square root E I m bar L fourth. Okay. And phi 1 is equal to sine pi x upon L. So, if I plot this, this is where this is of the form sine pi x by L. Okay. Omega 2 is equal to 4 pi squared E I upon m bar L fourth. Okay. And if you look at it, this is equal to so in this way, what we can do is we can find out, and I am not going into the next one, it is 9 pi and it will have 3. But note again one fundamental point that I made in the last time. First mode, lowest strain energy, no node. Second mode, slightly higher strain energy, one node. Similarly, if you look at the second one, it will be like this. Sorry. 2 nodes, higher mode, strain energy mode. And so, the point remains that the fundamental mode has the lowest strain energy mode shape. Okay. And as you go higher, the strain energy goes up, and so on and so forth. Okay. So, this is for a simply supported beam. Now, let us go on and look at the solution for a cantilever beam, because this is one beam. Remember, we solved the cantilever beam problem, and the cantilever beam was like this, and I am going to say that this has m bar EI. Remember, this problem we had solved for the specific case earlier. Okay. So, let us see what happens in this particular case. Note that we have the situation again, it is again phi fourth minus a fourth, phi equal to 0, and so we still have what? Phi of x. And note that let us not forget the fact that omega squared is equal to EI upon m bar into a fourth. This equation remains firm. This equation also B1 sin AX plus B2 cosine AX plus B3 sin hyperbolic AX plus B4 cosine hyperbolic AX. This is the the shape for a general simple beam vibration, flexural vibrations. The only thing that is different in each case is that the boundary conditions are different. In this particular case, what are the boundary conditions? At x equal to 0, we have phi equal to 0 equal to 0. Similarly, phi prime is equal to 0, and at this end what we have is EI phi 3 is equal to 0 and EI, both the moment and shear at that end are 0. Okay. So, these are the 4 boundary conditions at L and at L. These are the 4 boundary conditions. The first boundary condition we already know gives us the fact that B2 is equal to B4. Okay. And the other boundary condition, which is phi prime, we have already seen that phi prime is this becomes cosine and this becomes sine, this becomes cosine. So, what we have is that B2 is not equal to, is minus B4, and from this we get that B1 plus B3 is equal to 0. So, B1 is equal to minus B3. These two boundary conditions, this is given by this and this is given by this. Okay. So, if we plug these in, okay, our equation becomes the following, and our equation becomes phi of x, okay, B1 sin AX minus sin hyperbolic AX plus B2 cosine hyperbolic AX minus this is what we get. I mean, of course, this is the overall equation that we get. Okay. So, once we get this equation, then we substitute what? The fact that okay. So, if you look at this, these equations, now if you look at this phi of x, now if I look at it, phi prime of x is equal to B1 A, this will become cosine A, this will become cosine hyperbolic A plus B2A, this one become minus sine AX, and this will become minus sine hyperbolic AX is equal to B1 A squared minus cosine AX, minus sine AX minus sine AX plus B2 A squared minus cosine AX minus cosine hyperbolic AX, and similarly we get that phi 3 becomes equal to B1 A cubed, and the sine becomes cosine AX minus cosine hyperbolic AX plus B2 A cubed. This one becomes sine hyperbolic AX minus sine hyperbolic AX. Okay? So having done that, what do we get? We get the following. Substituting phi double 2, I get an L. Okay? This one, the A squared I can neglect, right? Because A squared is in both of them. So what I ultimately get is B1 into minus sine AL. This is phi double prime L is equal to this minus sine hyperbolic AL, okay, plus B2 minus cosine A minus cosine hyperbolic AL, and phi 3 L is equal to, again both of them have A3, and note that this is equal to 0, and similarly that's why A2 and this case A cubed disappear, and what we have is minus cosine AL minus cosine hyperbolic AL plus B2 sine AL minus sine hyperbolic AL is equal to 0. So this, you see, is two equations in B1 and B2, and I can solve this in this following manner. I can say that, look, note that both of these have minus in them, so I can take them on the other side, and what I have is the following. The equation looks like this. The first term, sine AL plus sine hyperbolic AL, okay. The second term, cosine AL plus cosine hyperbolic AL. This one, if you look at it, again this is what happens, that this one becomes plus plus and this becomes plus, this becomes minus. So what we get is cosine AL plus cosine hyperbolic AL, and this one becomes sine hyperbolic AL minus sine AL. B1 B2 is equal to 0 0. Now the only way this can happen is if this determinant is equal to 0. Okay, so this becomes what is known as the frequency equation. The frequency equation is the following: sine AL plus sine hyperbolic AL plus sine hyperbolic AL minus sine AL, okay, minus cosine AL plus cosine hyperbolic AL squared is equal to 0. This is the frequency equation that we have, and In the next class, I am going to show you how this equation can be solved for getting the cantilever free vibration frequencies and mode shapes. Thank you very much. Bye. See you next time.